So far, what we have looked at is that if I have a cavity inside a conductor and I put a charge or electric field outside that conductor, then electric field in the cavity is equal to zero. You would have electric field outside the conductor, but electric field inside the cavity is zero, and the cavity is shielding whatever you put inside from the external charges. Now the question comes, what happens if I put a charge inside the cavity? Instead of having charge outside the cavity, what we are interested in figuring out is that I go and I place some charge Q which is inside the cavity of that conductor. How would the electric field be created? Do I see any electric field outside? And how would the charges look like on the conductor? These are the questions we will try to answer. Because we have this charge is called a fixed charge. This charge is not allowed to move. I have somehow put this, maybe there is another material, which we'll see next week, and I have placed that charge in that material, and that material is sitting inside the cavity. So it is fixed in its position. We know our first rule was that electric field inside the conductor has to be zero. That rule has not been broken. That rule still needs to be obeyed. So anywhere I go inside the conductor, electric field has to be zero. So if I make a Gaussian surface, a closed Gaussian surface, and calculate the flux on this Gaussian surface, what I would get is simply electric field is zero, so it is simply an integral of 0 ds, and thus the total flux has to be zero, which tells you the net charge which is enclosed, that has to be zero. However, I have a charge Q sitting inside that cavity. What we are saying is that if we go to this red closed Gaussian surface, the total charge which is inside the surface, that should be zero. So there must be a charge of minus Q. There must be a charge of minus Q sitting somewhere else. We had another rule before that in a conductor, charge cannot sit in the volume. Charge can only sit on the surfaces. That rule is always obeyed too. So this minus Q charge would be distributed on the inside surface or of the conductor or the surface of the cavity. Right on that surface which I have, there must be minus Q charge. No ifs or buts about it. Gauss law has to be obeyed. Electric field inside the conductor is zero. And thus the net enclosed charge has to be 0, so there must be minus q charge, and a charge can only sit on surfaces of a conductor, so there must be a minus q charge sitting on the surface of that cavity, right on the cavity wall. Where does this charge ultimately come from? These are electrons which have hopped to reach the inside surface. So again, nothing can be created in the volume. Ultimately, these electrons are going to create vacancies in the outside surface. So there must be charge plus Q sitting on the outside surface. So there must be plus Q on outside surface. Right? The charge, again, we cannot destroy charge, we can only redistribute it. Some charge got pulled in to the inside part, to the cavity wall. Ultimately, it will leave some vacancies on the outside wall, and I should have whatever I pulled in, that many number of vacancies should be left on the outside wall. So there must be a plus Q charge sitting there. So what we have realized is that if I have a cavity inside a conductor and I put charge Q, we would end up getting charge minus Q on the inside surface and a charge plus Q on the outside surface. As we have talked before, this distribution will depend upon how charge Q is placed in the cavity. Is it placed symmetrically or asymmetrically? How does the cavity look? The charge which is present in the inside, that will depend upon how this Q is placed with respect to the cavity wall. The outside charge, remember what these two charges are doing. These charges are making the electric field go to zero in the conductor. The outside charge does not feel a force or does not get a force from the charges which are present inside, from charge Q and minus Q. The charge which is sitting outside and does not feel any force from there, the outside charge only distributes depending upon the shape of the cavity, the shape of the surface. That's what the outside charge will depend upon. We'll come back later to that point, how this distribution is going to be created, whether that distribution is going to be uniform or non-uniform, but the answer would only depend upon what the shape of the surface looks like. How does the electric field behave? Well, you are going to get an electric field. Assuming this charge Q is positive, there is going to be wind flowing from a fan to a vacuum, and all the previous rules we have talked about that these angles have to be 90 degrees. They have to be obeyed. That when they hit, the angle of the surface has to be obeyed. There is going to be electric field inside, and because I have charge sitting on the outside surface, there is going to be electric field which is going to be created outside too. There is electric field created outside when the charge is inside the cavity. This is the difference between a charge sitting outside and inside. When a charge is sitting outside a cavity, then electric field inside is zero. All the electric field which is created stays outside. There is no electric field being created. When I have a charge which I put inside the cavity, then there is electric field inside the cavity. There are charges which are induced on the surface of the cavity. So there would be minus Q charge sitting on this surface, and there would be plus Q charge sitting on the outside surface, and there would be electric field created outside too. A conductor shields the cavity from charges outside it. Whatever the charge outside is, I do not get any electric field inside this conducting cavity. However, a conductor doesn't shield the outside world from what is happening inside. If there is charge present inside, the conductor will not make the electric field go to zero in the outside world. It would shield the inside from the outside, but it doesn't shield the outside from the inside. Please keep that in mind. How this electric field would be created, how this charge would be distributed in the outside, we will take a look in after a few sections. But now let me ask you a question, and that gets to our next section. I want to shield the outside world too. So I have this charge Q. This has created a negative charge minus Q. And what I want to do is I want to create a condition such that the electric field outside is zero. Electric field only exists in the cavity. How can I do that? We have this charge which is present here. Till the charge is present on that outside part of the conductor, there is going to be an electric field which is going to be created outside. So somehow I have to remove this charge. How can I remove that charge? I can remove that charge by grounding the conductor. Let's understand what is ground, and from there see what is going to happen here. Ground is basically you take another piece of conductor and you attach it to the earth somewhere. Right? You want to see a ground, go to your basements and look at where the water pipe is coming inside to your house. You will see that at that place there would be a wire connected to the water pipe, and that wire is sunk into the earth. What we are assuming is this, that earth has infinite number of charges to give or take. That it is a source of charges, electrons, and if you need to sink electrons into it, it would happily take it too. It would give you whatever charge you need, or take whatever charge you want to give it to you without any problems. And what happens then is the potential of this ground is zero. We basically think of it, we have a conductor and we have connected it to our whole world, much larger. There are lots of charges here. If you have excess charges, it would happily take it. If you need charges, it will happily give you. And Earth is virtually sitting at infinity. This part, any part of the Earth is virtually sitting at infinity compared to the problem you have. So the potential is zero. Let's go back to our conducting cavity. So you have a charge Q which I put in the cavity, and let me ground this. You get electrons which are attracted, again assuming Q is a positive, resulting in minus Q charge here. But now because you have connected to the earth, assume earth to be a very large conductor, this minus Q charge is not ultimately hopping from this surface. This minus Q charge would hop from earth to the place where it wants to go. So the plus Q charge is, there is no plus Q charge sitting here. This plus Q charge is coming from your earth, from your ground. And now what you have, now the electric field outside is simply going to be zero within my problem. If you go and you make a Gaussian surface, you see you have charge Q and a minus Q inside. The total net charge is zero. And electric field here is already zero. So there would not be any electric field which would be created outside. When you ground this conductor, then you shield the outside world from the inside too. If you look at your signal generators or oscilloscopes, you will see that there is a case ground to it. That these signal generators and oscilloscopes are put in a metal box. They're not put in a plastic box. Plastic would have been so much cheaper than a metal. They are put in a metal box, and there there is a ground for the case. You can connect your ground to that case ground too. Why are we doing that? Your signal generators, oscilloscopes have lots of charges inside. We don't want that electric field to penetrate outside and affect your other circuits sitting close by. And thus, we ground the case. No electric field due to charges inside is now able to come out. That is your grounding. So again, let's re-emphasize, what does the ground do? It is acting like a very, very large conductor and a source or a sink for charges. Whatever amount of charges you want in your system, it's able to give you. Or if you want to go and reject some charges, throw away some charges, it would happily take that too. And the other thing is that when you have grounded, that surface becomes potential zero, which you can clearly see would be the case. You have electric field inside. Your electric field outside is zero. Once I have grounded it, I can walk on a path from infinity to this point. My potential here would be zero, and not only at the surface, any part of the conductor, the potential would be zero. I would get a zero potential. Let's take one of our previous examples and see what happens if we ground the conductor. We had previously put a charge Q outside. Let's just put a sphere with a cavity inside. And now I have grounded the surface of that sphere. This charge Q, again I'm assuming it is positive charge. This charge Q is going to start attracting electrons close to it, and the closer it is, the higher the density of electrons would be. Further away I go from this line, the density would become less. Previously we had seen that this negative charge was ultimately coming from the backside of the sphere. That these electrons moved and left some vacancies in the backside. However, now because we have grounded the surface, there is no positive charge left. There is no positive charge left on this part. These electrons are ultimately hopping from the ground till they reach the place they want to. What would happen is that electron from one atom here would hop in, leaving a space. There would be another electron which would come and fill it, another which would fill it, and this hop process will continue, and ultimately whatever vacancies are left, electrons from the ground will come in and fill that vacancy, keeping the back part to be neutral. For this calculating or plotting the electric field lines are now simply going to look like positive and it's going to look like that. Previously, we had seen there was an electric field lines in this region, in the region in the back. Now, this conductor is shielding that region. Electric field lines just behind that is going to be zero. It is as if this conductor is creating a shadow behind it. That the lines would simply remain like that. There would be a region behind the conductor where electric field lines would be zero. Electric field would be a zero there. That is what happens when we ground a conductor.